It's just me being me. I don't know. It's like a waste. So if somebody wants typo bonus, you could say on page 3, I believe, number 1, change the problem. And you don't have to tell me what to change it to. If you have a suggestion of what to change it to, by all means. But I just need to, I need a prompt, a reminder to actually sit in front of a computer and make the change. And again, typos, you submit those through the Remind app. So you send me a message, and keep it simple. You don't have like, greetings, professor, hope you're having a wonderful, no, I don't need any of that. I'd appreciate it, like it's nice if you send it, but that's going to cost you time if somebody else is submitting a typo. If you want to say nice things to me, I'm right here. You can do that at any time. When it comes to submitting typos, just open a message, and some people take a picture of it. Just buy themselves time, send the picture and say, fix question number 2. Okay, so page 3, question number 1 in this case, change the problem. That's all I need. All right. All right, number 2. Well, it's not a power rule problem at first glance, but if we make a minor adjustment, it will be. Yeah, x to the negative 4th. And this is what I was talking about before, where you don't really need to know the rule of x to the n plus 1 over n plus 1, as long as you have it in your mind that when I take the antiderivative of a power function, I'm going to increase the exponent by 1, and then divide by whatever that new exponent is. All right, so increase a negative 4 by 1. The number of people who get that wrong is always astonishing. And then divide by the new exponent, and then the plus c. I'll get a lot of x to the negative 5th. Oh, because if you think of the power rule in Calc 1, we would always multiply the power by the coefficient and then reduce the power by 1. Here, we're doing the exact opposite. We're increasing the power by 1 and then dividing by the new exponent. Right? So if you had, let's say, I'll use my x squared example. So in Calc 1, we would do a derivative. It would be multiply and then add. All right, so we would get, oh, sorry, subtract. 2x to the first power, all right? Now, we're going the other way, where we're taking something like, well, I'll go x squared again. So, Calc 2 is the antiderivative. We're doing the exact opposite, right? So, in the exact opposite order. So, here, when we were taking the derivative, we multiplied first, then we subtracted. So I'm going to do the opposite of that. The opposite operations in the opposite order. So the last thing I did here was subtract a 1. So the first thing I'm going to do here is add a 1. The first thing I did here was to multiply. The last thing I do here is going to be to do the opposite of multiply, which is divide. And that would be by whatever that new exponent is. And so we get x to the 3rd over 3. 2 times the 1. Yeah, power by coefficient always, yes. All right, and like I said, for number 2, if you want to clean it up, you can. I guess you should be prepared to. It'd be negative 1/3 x to the negative 3rd plus c. Because you have the understood coefficient of 1 in front of the x.
It doesn't matter if you put like the x together with the 3 on the bottom, right? As it being negative 1 over 3x to the 3rd.
As long as it's a positive 3 when you put it in the bottom. Yeah. Then it's okay. But if you leave it as a negative 3rd, then you'd have a problem. Because it's
side switch. you just separate things.
Right. All right. So, yeah, and negative exponents are perfectly fine. Don't feel the need to change out a negative exponent form. I always thought that that was kind of an awful joke that was pulled on people. Like in algebra courses, let's teach you about negative exponents and then tell you that you can never use them. Like, they're the best things ever. When you write something in a negative exponent form, it saves you so much time and energy. It's like, wait, using a negative exponent, I completely dismiss the concept of division? I can ignore 1/4 of mathematics? Like, why am I not doing this for everything? And so yeah, just leave it as a negative exponent. Don't feel the need. And besides, if you have to do something with it, odds are it's either another antiderivative, in which case you want it in that form, or it's number crunching, in which case you're going to get the calculator involved anyway. So what purpose are you serving by making it a positive exponent and changing things up? Right? So keep that in mind. And anytime you think about a next step in a problem, ask yourself, what purpose does this serve? Now, a correct answer to that question would be to answer the question that was posed on the test. Like, I was told to do this, so the purpose is to get full credit. That's the exception. But if it's like you're doing it to meet your own needs, then really ask yourself, is this what you really want? I don't think it is. So we have, going back to Calc 1, you had constant multiple rules. You had product rules, quotient rules, sum and difference rules. You had a rule for everything. But just focusing right now on the what we call the constant multiple rule. All right, it exists for limits, derivatives, antiderivatives, and summations. So anything that could possibly be relevant in this course. And all it tells us is that if there's a constant multiple, so a coefficient, a numerical coefficient, not variable related, that it doesn't need to be there, it can be factored out. Some of you are pros already at antiderivatives. Some of you have never seen one before tonight. Everybody else is somewhere in the middle. So you might have different thoughts on how you want to go about doing this. Some of you can look at the problem and say, oh, well, I don't need to pull out the 5 in order to come up with the answer. I'm not telling you have to do it this way. This is an approach that you could take because, and especially if you're a novice, if you're not comfortable, familiar with antiderivatives yet, then you're still like referencing tables and things like that. Like that previous page, you look at antiderivative cosine of x dx, you're like, okay, let me flip back to the previous page, see what that was. I'll get around to studying it later. I'll know it before the test, but for now, let me just reference it. If you're that person, then this is a good move for you, pulling out the 5, because now you can look at this, and this corresponds directly with something that was in your table. All right, we now know that just this component, that's negative sine x plus c. Then we have the 5 on the outside. You can leave it like that if you want. If the question doesn't say simplify, I'm done. But if it does, then what I want to do is distribute. All right. Is it positive? Oh, crikey. Thank you. I was too busy being inspirational to fact check. Fortunately, you're all inspired, so most of you didn't notice. So distribute the 5, and you get 5 times the sine of x plus c. Yeah, so that's the weird component there, and that'll be a recurring theme. You would think, but c, the constant of integration c, is of some constant. And since 5 itself is a constant, if I multiply two constants together, I'm just getting another constant. Okay.
Would it be wrong if you put 5c, or?
Only if I said to simplify. If I said to simplify, I can leave it at 5c, then not. But it's one of those come on kind of incorrects. Like I take off the quarter of a point, you get the test, you say come on, and then you come back to me like, we really have to do this. I learned my lesson. I won't do it again. We can still have that conversation. I'll probably give the quarter point back, but it really is technically incorrect if you write 5C. All right. Technically incorrect if you write 5C. This is the correct answer. Right, but it's a constant, since it's a general term that represents a constant, if you multiply it together with another constant, it's still a general constant.
And the 5 is like we're saying 5 times that constant eventually.
It's still another constant, yeah. You got to think of C as well, they call it the absorbing constant because it absorbs all other constants. So if I multiply C by any other type of constant, it could even be constant K, like on the previous page, it's going to absorb any other constant. So if I multiply C by 2, multiply C by K, raise C to the third power, anything like that, the result is always going to be C. Right? And some of our formulas and constructs, I guess, will break down. Like Newton's law of cooling, when we get to it, won't work unless that is a truth, the absorbing constant. The constant comes from the idea that when you take the derivative of 5 times the sine of x, you will get 5 cosine of x, but you could also take the derivative of 5 sine x plus 3 and get that same thing. Or 5 sine x plus 20 and get the same thing. So we're allowing C to be some general constant that could exist. But we just don't know what it is because it could be anything. Number 4 is a little bit of a twist on it. It's actually an equation, a differential equation that's in polar form. Polar equations are not part of this course. But if you think of it, it's following the same form as dy dx. You think of the r as a y and the theta as an x, then it's fine. We're not going to learn in this course how to convert back and forth between the 2 different numerical systems, so it's still a good problem. But anyway, solving a differential equation, first you want to get it into differential form, which means split your d's up. All right, so I want dr by itself. I'm going to think of that pi as a pi over 1, and then I'm going to cross multiply. All right, so dr would be equal to pi times d theta. I like to mix this kind of problem in there so you don't fall in love with just y's and x's, because we're going to move away from that pretty frequently. All right, so what I want to do is find the antiderivative. But of what? Well, of everything. So I'm going to throw in a little 1 here in front of the dr, because you kind of fall in love with the idea of dy, dx, dr, whatever, it doesn't matter, as being just notation, but it's really not. It's a value, and in some cases it's an operator. So what we have here, whenever we see a dy or dr, is 1 times dr. When we get into the physical manifestation of that, it'll be more obvious. I'm going to take the antiderivative of both sides. So I'm integrating 1 with respect to r, and I'm integrating pi with respect to theta. All right? So on the left-hand side, I would just say, well, what's the if the relevant variable is r, what would be the antiderivative of 1? R, right? R plus c. On the right, I'll do a slight little maneuver real quick. I'm going to factor out the pi, because that's a constant. Constant multiple allows me to do that, constant multiple rule. Antiderivative of 1 d theta. All right, so forget about the pi for a second. I'm just focusing on this. This bad boy right now. What's the antiderivative of 1 with respect to theta? What do we say? Theta, yeah, theta plus c. We'll streamline the process a little bit in a second because we got c's all over the place. We got a lot of fluff here that we don't necessarily need. But to develop the underlying concept, I think it makes sense to do it at least once. All right. So on the right-hand side, we're going to do something very similar to what we did in number 3, and then we'll consolidate our c's. All right. So we're looking at r plus c equals pi theta plus c, right? Because I'm distributing. Constant times a constant is a constant. Now, some people, I don't think any of my teachers were like this, but, and really I only know this because I've had students tell me that their teachers insisted that they do this, that they subscript, that they indicate that these are different c's from one another by doing a sub 1 and a sub 2 here. I don't think that's necessary, as long as you have it as a conceptual understanding. But what I'm going to do is I am going to subtract c from both sides. Now, here's the big question. What is c minus c? C. All right, so this could play out one of two ways. You look at it and say, well, they're not necessarily the same c. So if that's the case, the difference is going to be some constant, right? So if this is 3 and that's 2, then I would get a 1, which is a constant. But let's say they are the same constant. C minus c is 0, which is a constant. A constant 0, I mean, it's the definition of constant, right? It's an unnecessary constant in that case, but I can't guarantee that it's going to be 0, so I still want to cover myself by saying that some unknown constant can be added off at the end. What that gets me to is the idea that I never had to write the plus c on the left-hand side to begin with. All right. So when I take the antiderivative of a differential equation, so I'm solving a differential equation. When I have a dy term on the left-hand side all by itself and I integrate it, that's going to give you a y. Just like the dr gave me an r. I don't need to put plus c there because all it's going to do is get combined with the other c, the c on the other side, to make one negative c. I don't know, or mini c, depending on the c. I don't know how you feel about c, but that's the idea there. So it allows us to streamline the process. Also, we get from this the idea that the interaction of the c is really kind of irrelevant when you're just focusing on an expression. So when I pulled out the 5 in number 3, integrated, I had the plus c here and then distributed. What I kind of learned from this is that instead of doing that, I can take the antiderivative of the cosine of x, get the sine of x, multiply it by 5, and then later on tack on a plus c at the end. Right? All of this is for the idea that you can just say, let me do all the work first, and then when I'm done with the problem, put a plus c at the end. Because it's all going to come out in the wash anyway. Right? So, but if you want to make sure that you keep track of those like minor details along the way, because that's just in your personality, then by all means do so. But I don't know that it's always necessary. All right. Number 5, we have a rational expression here. We haven't learned use substitution or anything like that yet, so we're not doing that. It's got to be simpler. Here I could actually split my fraction up. Let's split. And that might be what makes the course hard. When people say it's hard, it might be because of something like this, where you have a problem, it's presented to you, you look at it, and you say, Now what? Is it a power rule? Is it a integration by parts? Is it a partial fractions? Is it like trig substitution? What am I working with here? Time. Time becomes a major component. If you can recognize similarities among problems, that ends up being a time saver. Because if you can't, you end up saying, well, I don't know what to do here, so let me try this. 15 minutes later, you realize that was not the right way to go. So then you try something else. There's only so many groupings of 15 minutes that you have available to you during a test. So you waste too much time trying to diagnose a problem, you run into trouble. All right. So at this point, you're taking a test, you're looking at this problem, you still may not even be convinced that you're going about this the right way. Simplify. The simplify that I don't tell you to do. You just figure out, well, that's got to be the next step, otherwise I'm stuck. Keep the base, subtract the exponents. We're going to have x to the negative second. 2x to the negative third if I subtract these guys. Well, let me not circle that. There's an understood 1 here, that I'll circle. All right. So the second one would be 2x to the negative third minus, now the last one there, we have an understood x to the 0th attached to the 3. So that one would be 3x to the negative 4th. Yes. All right, so in Calc 1, we had a sum and difference rule for derivatives, which meant that if you had expressions that were separated only by addition and subtraction, you could break it up, take the derivative of each guy separately, then bring it all back together later on. Didn't work that way for multiplication and division, but for addition and subtraction, it was great. It was the only thing that made it work. Same thing comes into play for antiderivatives. We can take the antiderivative of each part separately. So whether you actually want to write that out is up to you. I'll write it out just this one time. But once you get a good handle on this stuff, you realize that just takes too much time. You have the problem figured out before you even get halfway through writing that mess out. All right, but each one of them is a power rule. Now, for power rule, I think personally, like in numbers 3 and 4, where we pulled out a coefficient, power rule, I don't think it's worth it to pull out the coefficient. In 3 and 4, I think it was fine because you were dealing with transcendental functions. You were dealing with something that was not algebraic. Okay? Trig functions, log functions, things like that. Get rid of the coefficient. It makes things too messy. But when you're dealing with polynomials, the coefficients are all right because if you follow the process of increasing the exponent by 1, dividing by the new exponent, it's all going to work out. X to the negative second, increase that by 1, you get x to the negative first, divide by the new exponent, so divide by the negative 1. Increase the negative 3 by 1, you get x to the negative second. Divide by the new exponent. The new exponent is negative 2. 2 divided by negative 2 is negative 1. I'm going to carry down that plus sign that was there. I get a minus sign to carry down over here. Increase the 4 by 1, you get a negative 3, so x to the negative third. Divide 3 by negative 3, you get negative 1. You leave it like that, it's fine. Or you could just clean it up a smidge. Do all your housekeeping first before you put the plus c on. So negative x to the negative first minus x to the negative second plus x to the negative third plus c. All right. These problems, I mean, I won't call them easy, because that's pretty frustrating for the folks that don't find it easy. But I'll say it's more basic than some of the problems that we're going to do down the line. Not an unfair statement, because of course it's always going to get more difficult as we go. So for now, if you were to write the plus c after each one, and then do your simplification with a plus c after each one, and then combine them later on, it's not the end of the world. But there will be some problems where if you introduce the plus c too early, it just makes the amount of writing that you have to do so much worse, to the point where it's aggravating. So save it for later. So with that being said, I'm going to put stars on 6, 7, and 8 because now you have everything you need to be able to try those problems on your own. All right? And we'll go over those next class. I want to go over one more small topic before we end for tonight. Oh, 2 stars on that. 3 stars. Whoa, this must be hard.
Isn't that a different rule than an 8, or is it?
You would think
We should still be able to do it.
you should still be able to do it, yeah. But since we haven't learned to do substitution, integration by parts, or any of that stuff, if we're only limited to the rules that we talked about on the previous page, then there's really only one thing that you can do to get yourself started on this problem. This one? Oh, that's this guy here? Yeah, so I took that term, put it over x to the 4th, then 2x over x to the 4th, and then I put the negative in front, so it's a positive 3 over x to the 4th.
So 3 over x to the 4th.
Yes.
So is that x?
This is the 4.
And
Here?
3x.
Oh, then, yeah, x to the 0th power. Yeah, just to indicate what the power would be when we were subtracting.